Now we come to the third presenter, our keynote speaker here, Professor Bilad. Are you with us?
Yes.
Yes, right. All right. As I mentioned previously, that we will very appreciate if you keep the time for your talk for at 20 minutes, Professor Bilad. Now we can start your talk.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. First of all, thank you for the committee. Thank you, Prof. Aris, for inviting me to share my ideas, I would say, in this conference. It is always hard to prepare materials for this kind of conference, quite general. Yet at the same time, we don't want to waste everybody's time, right? So I would suggest you to look into what I'm delivering. I don't expect you all to comprehend and understand everything, but it is the time for us to look an opportunity to collaborate later on. Even though you are from, for example, educational research, I think you can look into what I'm delivering and then find out how can we work together and engage later on. As introduced, I'm from Chemical and Process Engineering, University Brunei Darussalam. This is a beautiful building where I'm working now. It's called Integrated Science Building, Faculty of Integrated Technologies in JBD. And we have like 20 postgraduate scholarship every year. And I'm inviting you, if you incline to do postgraduate studies like a PhD. We are really open, especially to ASEAN countries. And for me, I'm trained on membrane bioreactors, but along the way, I've expanded my research to different fields, including what was presented by Prof. Nazaruddin in the beginning, use of biomass. So this is a kind of nexus of how I conduct my research, or what are my interests in research. But today, what I want to present is more on ideas of how to the approaches that can be used to develop process based on porous thin membrane materials. So it is logical then to first brief you in general about what is membrane material we are talking about and how it is assembled into industrial scale models. I will touch a bit about the established processes where this material is fastly used. And then in the end, I will share a few ideas of what I'm currently doing, what I have been done, and ideas of research I'm planning to do in the future. So membrane generally is defined as it's a layer that separates two phases. For example, here we have one phase here, okay, and we have another phase on the right side. And the membrane is something in between that allows the separation of the two phases. The material look like a paper. You see like a paper here. This is what appears when you use a camera or your naked eyes. But if you look under sophisticated tools like scanning electron microscopy, you will see it consists of a lot of holes. So any black dots you see in this image is basically pore, membrane pore. And then typically there are 2 to 5 million of pore in a square centimeter of membrane surface. To make it is quite easy, this video is actually part of my work collaboration with Prof. Aris and Prof. Susi from UNRAM. It starts with a polymer solution. I'm talking about polymer here. We cast it into a film using a simple casting device. Here we just use a glass with some modification. We bring it to the non-solvent, which is water, and then the polymer solidify to form a thin layer. on top of non-woven support. So it's quite easy. And then for your information, this membrane material was made from the waste of a cigarette filter. Indonesia is heaven for smokers, so they throw away the filter. We collect the filter and then we dissolve it into with some solvent, and then we make it into a membrane. So that is this video come from. So those are what appears in the small scale. In the large scale, we call it membrane modules. We make there are some design. This is an example of tubular membrane. Okay, another one. Okay, and this is an example of flat sheet membrane. So it's like flat like a piece of paper, the one that I saw earlier. And this called I think it's hollow fiber based membrane. I will not talk into detail. So basically, in research, we use a very small scale, but when we scale it up into industry, it looks completely different. So what are those applications? Okay, the most common thing we know is for water and wastewater treatment. I think 80% of seawater desalination is achieved currently by what we call as reverse osmosis. Okay, it is heavily used by countries in Middle East. It is now even used in Southeast Asia. I think 60% of water in Singapore treated by reverse osmosis from seawater. Okay, and there are many. Maybe you are quite familiar with it. Reverse osmosis is probably the most common. There is a called nanofiltration, ultrafiltration, microfiltration. The take-home message is that the membrane that I've shown in earlier slide can be modified to different pore size, and then can lead to different application. Okay. It is believed that membrane process will be the key technologies that address the future water problem. Okay, the key technologies here is for disinfection, removing virus, bacteria from your water, decontamination of water. It can be used to reuse the wastewater, and of course for desalination of water. Yeah. Okay, another interesting application. I hope none of us will have to use this device, but maybe you don't realize that this device is used in some of people that daily life, which is for we call it hemodialysis. Basically, some patients they have kidney failure. And basically, the kidney doesn't function. Kidney function is to filter the blood. So the mechanism of how it works is you have a semi-permeable membrane, porous membrane, like here. So it's just an example of bag. Inside the bag, you have a globular, it's a protein and ionic contaminants. So you can relate to the hemodialysis application. The protein is the blood, the cell blood. And then ionic contaminant is uric acid. Normally we waste through when we pee, okay? So, so the membrane is basically replacing the function of kidney. And of course, we cannot bring into the body. There is a precision pump used to pump through this called dialyzer, which is made from membrane. And the membrane used here look like this if you look it under microscope electron. Okay. These are the, I think, two most used application in membrane. So what are new? So last few years, I've been working on oil water separation. So how can we separate oil from water? One of the most common thing you've seen is, for example, in santan. So santan is when you process the coconut. See, the coconut is a mixture of water and oil. So it's look like milky, but it's basically a blend of water and oil that form stable emulsions. We try to break those emulsions. Okay, and then another idea I want to share is membrane rotating, biological contactor, and fault osmosis electrolysis. Okay, so all of these three applications use this porous separator. So traditionally, okay, the way we treat oily wastewater is through at least three stages. Okay, they use a tilted separator, that's to separate the oil, and then they use air bubble to float the bubble. This is how the unit look like. You can have a more compact tilted plate. You can have a horizontal long vessel like this. Then it uses micro bubbles, air bubbles, to float the oil. So bubble will interact with oil droplet, and then since the bubble has a very low density compared to the water, it will rise up and float. And then in the end, you still need to polish whatever you have using a membrane separation, like the one we do for water. Okay, and this is the idea we applied. So instead of having 3 separate units, we can actually install the separator. Okay, install the membrane in the separator, and then use the pump to suck the water, so that we can have what we call as achieve a process intensification, where we can combine membrane with the dissolved air flotation and tilted separator. In conventional way, we will need a lot of stages in treating wastewater. For example, we need pre-treatment, we got a primary treatment, secondary treatment, tertiary treatment to achieve clean water that is safe to discharge. With this idea, we can intensify the process and achieve what we want in faster and more simple stages. Okay, with those are the concepts that you are still developing. We have a few results on well water separation, but what we have so far is we use the same concept to filter microalgae. Okay, basically to enhance the efficiency of those bubble to clean anything that's stuck on the surface of the membrane, and we achieve a substantially higher filtration. You see here that the filtration rate is almost double if we put it in using a tilted separator. Okay, we do some modification and some optimization process to maximize the system. Okay, how can we achieve maximum by using some of the simple simulation. Okay, and we apply that one to different application. Initially, we developed it for microalgae filtration. We have tested to also for treating wastewater in membrane bioreactor. Okay, the next is membrane rotating biological contactor. What it is? This is a conventional way of treating wastewater. We use a film. Basically in treating wastewater, we have microorganisms that consume the pollutant in your waste. Okay, and then the microbe normally will form a flux or stick on some surface, and then in achieving the degradation, they need oxygen. So in this rotation, for example, here I can show you the video. This is how it works. So when it goes down, okay, submerged in the water, they perform the pollutant degradation. When it goes up, the oxygen is dissolved to the system. The problem with this is that later on the problem with this one is later on you will have some of the washout of the pollutant that need another treatment. Normally we have a clarifier in the end. Okay, so what we have done in our work is actually to develop to involve membrane in it. So what we do is to install a membrane in between this plate. That's the idea. So to put a separation in this plate, this is the membrane in this plate, and it will be able to intensify the process, and the rotation that otherwise only used to supply oxygen to the system now can be used also to clean the membrane and achieve much better performance as seen in this slide. Inspired by this idea, we then apply this one for oil water filtration and perform some simulation. And yeah, you see here the productivity increased by around 40 to 50%. Okay, I'm out of time. Finally, it's a forward osmosis electrolysis. So what is that? First of all, I'll discuss a bit about forward osmosis. It's basically an osmosis process that we okay, so what is it? We have, for example, a contaminated water coming to the system, to the membrane. Okay, in this video, this is the contaminated water. Okay, and on the other side of the membrane, we have a solution with a high solute concentration. For example, this is the fresh water, wastewater, and this is the seawater. Because of the osmotic difference, as you see here, the volume of the fluid here is decreasing over time because of the water permeation. So this is called forward osmosis process. And electrolysis is a quite simple process. When you use electricity to break water into the oxygen gas and hydrogen gas, this process unfortunately is energy intensive. But people have dreamed of having a car with water as the fuel. This is one of the step that can be used. So what it is, how we use this membrane in this process intensification. So we try to combine the forward osmosis in this aspect with the electrolysis in the right hand. So in electrolysis, we need some of the electrolytes. The electrolyte used in the electrolysis is used to draw water in forward osmosis. As you can see from this simulation, you see we can concentrate it wastewater and then draw the water to the electrolysis and use and break the water to produce hydrogen and oxygen gases. So these are reaction what happening in the cathode, what happening in the anode. And the dream is basically we can, for example, produce during the oil water production, we have complex wastewater. Okay, we can send it to the forward osmosis electrolysis cell. Okay, and the water from this waste will be drawn to the electrolysis cell and split to produce oxygen and hydrogen. Okay, that's all of my presentation. I hope I keep my time well. I hope I can share ideas and looking forward to discuss and for future collaboration. Thank you, Mr. Chairman.
Thank you, Professor Bilad. Ladies and gentlemen, now it comes to the time for the discussion for the keynote speakers. For the first part of the questions, I will open about 3 questions to ask the question to either the keynote speakers. Before you mention the question, please what is it? Provide your names and your affiliation, and the question is for which keynote speakers. Okay, let me open the question. Any questions? All right, before maybe later on. I just for Professor Wei.
Yes.
Are you with us, Professor Wei?
Yes.
All right. Yeah. I just I want to know your suggestion. If you run such experiment and sophisticated experiment, and we face in some places that we face a shortage of facilities, it is costly to run your experiments.
Sorry, I don't get. Can you repeat that again?
That I imagine that to run the experiment you have presented earlier, that it will cost a lot of budget.
Yeah.
Facing that in some areas here we face limited resources. What any suggestion you can give us for? Is it possible to run such experiment in this limited?
I think okay. This kind of machine learning approach is very general, and once you can use the Dennison theory to do the calculations, okay, and then you can to train the potentials, and such that you can do the calculation by sacrifice 2 or 3% accuracy, but you can do some material system with more than 1,000 atoms or 100,000 atoms, okay, and which is doable. And with that, you might have a possibility to predict the material property quite accurate, which may close to the experimental measurement. Okay, so I would say, generally speaking, this kind of approach would be applied to quite a lot of areas. Okay, for example, lithium-ion battery, we are currently focusing on this part and try to study how the lithium behavior inside this kind of lithium-ion battery materials. Okay, yeah, but I believe all the approach can be used in all the other cases. Yeah.
All right, thank you very much. Now I invite other expert participants to ask the question. Okay, Professor Nazaruddin. Yes, you can.
Because no one asked me the question, because for the professor from Taiwan,
Yes.
Professor Bilad, Taiwan.
Yes, thank you.
Yeah. The presentation is very interesting. I just remember I have two friends when I was Ph.D. student, and they are from Taiwan. One of them is in Tsinghua University.
Tsinghua, okay.
Yeah, Tsinghua University. And two of my friends is work also similar like you, computational chemistry, and they use a material studio to that. And when I was in London, UCL University of London, this is related with the chairman and moderator. They use Metro Studio, and this require a supercomputer to calculate all the things they want to do. So, could you explain what kind of software you use it? Because if I try to run my Metro Studio in my computer, it's not enough capacity in my computer. What kind of software?
Okay. I think a Material Studio is a Dennison theory code, actually original from Cambridge Group, TCN Cambridge Group. Okay, and we all know that the Dennison theory can handle a system with only 100 of atoms. Okay, and if the system inside unit cell more than 100 or 1,000, it's very painful to do this kind of DFT calculations. And so that's the Dennison theory are very limited to do the large scale material studies. Okay, So the recent development of the machine learning approach, which can using this kind of training data generated by the Denver series. Okay, for example, we usually generate the Denver series with the so-called Vienna ab initio simulation package, which can easily done a few hundred to 1,000 atoms. Okay, and so in that sense, we can generate the database for the machine learning training. And usually, if also machine training program, we use a so-called MD package, which is based on so-called momentum tensor potentials. Okay, it's a very well-written code and very friendly. Okay, so if you are familiar with these kind of things, okay, you know how to generate the DFT training data set, and then you familiar with the so-called MD code, and which you usually can within 1 week or sometimes simple system, you can generate a machine interacting potential, which is with the accuracy of 2 to 3 or 4% of the compared to the densified series. Okay, and its computing time will faster than 1 million times, something like that. Okay, and which will, with this machine interacting potential, which will really powerful in doing this all the other kind of simulation you like. For example, is typically you can generate a system with 10,000 atoms. Okay, and with a modern size computer, like you have a machine of 32 code. For these kind of things, you can do the MD simulation, maybe something like 500 picosecond or 1 nanosecond in 1 day. Okay, that means 10,000 atoms and only in 1 day. Okay, yeah, and that the result is very close to the DFT results. Okay, so you can imagine that how powerful it is kind of machine learning approach. Okay, yeah, so I will encourage people, everybody, like jump into the field. Okay, and there are so many kind of open source code for the machine learning approach. Okay, and so also they are also a very open friendly source code like a densified series, like a quantum express, so the developed by the Italian group. Okay, and so if you put some time into this field, you will become expert for this kind of things. Okay, thank you.
Okay, thank you, Professor Ray. I invite also the participants to raise the questions. Any question from the participant? All right, Alfred.
Okay, thank you very much, moderator, for this opportunity. Prof. Wei, I'm very interested in your research, and I would like to ask how to learning machine. How many data you have used to make your machine learning can understand the process you want to
okay. I will say it depends on your system size. Okay, for example, I will usually say generally 100,000 or 200 or 3,000 or even 1 million of the force in the DFTs. Okay, so if I have a system of this 1,000 atom inside unit cell, and so each time frame I will have a 3,000 forces. Okay, and if I use the a few hundred time step of the MD simulation. Okay, so that's I will have enough data set for generating the machine learning interacting potential. because for this kind of machine learning interacting potential, usually they have only a few thousand parameters. Okay, so if you use the 100 times of the force, then usually you can have mimic a very good interacting potentials. Okay, so let me say, okay, you generate the DFT by using a few hundred data, okay, which may be generated by 500 or a few 2,000 or 5,000 time steps, okay, and then select the 1,000 time step from the MD simulation and as a training data set. So that's it. Okay, so the DFT, of course, is not the trick, but you do it once, okay, and then do the MD simulation, MD training, okay, and which you are expert, okay, and you can train it within 1 week, or sometimes you can simple system. You can either 2 days you can fit the potential, and for long times, okay. So I really encourage people doing that, okay. Even let me put on this way. Even in our institute, we have everybody. On average, we have some 5,000. We have a total computing core roughly 5,000 in our institute. Okay, and everybody might have 1,000 core per group. However, we cannot do the DFT simulation for really complicated system. Okay, but with this kind of machine learning approach, okay, even you have only 200 cores, okay, I think you can handle a system something like a few thousand atoms. It's very easy to achieve. Okay, yeah, so that's my suggestion, and I will encourage everybody jump into this kind of machine learning approach. Yeah.
Thank you very much, Professor Roil. I hope someday I can visit you, because my son is also in Tsinghua University.
Yeah, okay, good.
Energy technology.
Sure.
Learning about energy in Tsinghua University, my son.
Yeah.
And someday,
please, okay, if you are interested to bring our institute, just okay, send me the emails, okay? Yeah.
Thank you, Prof.
We can maybe later we have a chance to form some collaboration project. Yeah.
Thank you very much for your answer.
Sure.
Great.
Yes, is there any questions? But let me give for the online participants. They raise a questions. Are there any questions from the online? No? Online. All right. Professor Aris, please.
Okay, thank you, Bapak Profesor Agus Abibulwoko. Hello, Dr. Wei. How are you today?
Yes.
Okay, I'm Aris. Always chatting with you for this conference.
Yes.
Dr. Wei, I'm interested with your research. In my mind, there are a question for you. The patient have attack in online. I'm interested in your research with machine learning from the theory and the experiment result found. What percentage of deviation are obtained? One question. And another question, will one day machine learning have feeling of sadness, happiness, anger, that human feeling? How to create such a condition, Dr. Wei?
excuse me, could you briefly repeat the question again?
Okay. Yeah, my question. From the theory and experiment result found, what percentage of deviation are obtained? That's one question. And another question, will one day machine learning have a feeling of sadness, happiness, and anger like human feeling? How to create such condition in machine learning? Thank you.
Okay. Okay, then let me plot this way. Okay, if you want to do a simulation for interpretation data for the experimental data, okay, typically we need to have some overlap between the experimental measurement and also the theoretical calculations. Okay, frankly speaking, usually the data we have been obtained from experiment is too complicated to study. Most of the time that the structure is not known, or the structure is too complicated, and then this kind of even the structure is known from experiment. However, the very accurate calculation run by density function theory, which usually limit by 100 atoms or 200 atoms, and under the condition you have a huge computing power, then you may have some overlap between the experimental. So you have the first thing, you need a very accurate experimental measurement. Okay, you have a single crystal, and you know the very good structures, and then you have very good measurement with the, for example, photo emission. You need to have some angle dependence. Okay, this kind of K-point dependence, and then for the DFT, you can only calculate maybe 100 atoms. Okay, so if for example, if you have a very big unit cell, then there's no overlap at all of the experimental data and the theory. Okay, but I think the machine learning approach somehow is bridging these two experimental and the DFTs. Okay, at least for the structural model, and because by training that the things, okay, you can really you can increase the computing time for the structural model by 100,000 or even higher speed. Okay, so that means that you can easily to obtain the structure and get the material property from that. For example, you can do the phonon calculation or something like that, and you can really treat the materials in the measure in the experiment. Okay, and so I'm not saying that is very but it's at least bridging the experimental data and the theory calculation, which you can have some link. You can have overlap to the experiment and theory to studies and to work together. Okay, yeah. So that's it. Yeah.
All right. Thank you, Professor Wei. That's a very interesting discussion, but I'm sorry that we have to stop our discussion here because the time has passed several minutes from the schedule. So let's give final applause to our keynote speakers. Thank you for all keynote speakers, Professor Ray, Professor Nazaruddin, and Professor Bilad. And I apologize for any inconvenience in hosting the discussion and presentation at this time. Thank you very much, and the time is now for the committee. Thank you.
Thank you. Thank you, Professor Abdi, as the moderator today. And please give a big applause to our keynote speakers today. All right. Thank you. Ladies and gentlemen, before we come to the second keynote speaker session, we are going to give a token of appreciation to our three keynote speakers. To Mr. Nazaruddin, SST, MSc, Ph.D. Here is the certificate as the keynote speaker of second ICSES 2022. Please give a big applause. And also, we are going to give a token of appreciation to Mr. Nazaruddin. We'd like to ask you to come forward. And Professor Abi will give the token of appreciation to Mr. Nazaruddin. Okay, please give a big applause. Thank you so much. Thank you, Mr. Nazaruddin. Thank you, Professor Abi. And also, this is the certificate to Dr. Ching Ming Wei. Thank you so much. We give a very great thank you to Dr. Ching Ming Wei from Institute of Atomic and Molecular Sciences, Academia Sinica, Taiwan. Please give a big applause. We really say thank you for coming on our second international conference. And also to Dr. Muhammad Roil Bilad. Here is the certificate as a keynote speaker from second ICSES 2022. Please give a big applause to Dr. Muhammad Roil Bilad. Thank you so much, Dr. Muhammad Roil Bilad, for coming to our second international conference.
All right.